Alright, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 3 here, which is asking us determine the tension developed in cables AB, AC and AD. Right, now this is a similar problem to F3-7 and F3-8, which I've done tutorials for earlier. So if working in 3D space like this is new to you, I'd suggest maybe consider having a look at those previous tutorials. Anyway, we're working in 3D space here. Now, I am drawn to the tension in AD. The reason I'm drawn to the tension in AD is because that is the only force we have here working in all three dimensions. It's got an X component, a Y component, and a Z component, right? Now, what's interesting about this is that it's almost like we're working with a three-dimensional version of this kind of 3-4-5 triangle idea here, which I'm assuming that you guys have come across before. And I trust that you guys are aware of how we can kind of break a force like this down into, in this instance, 3/5 of the magnitude is its X component and 4/5 of the magnitude is its Y component. I've kind of generalized it on the right-hand side here. In this instance, it's almost like we have the 3, we have the 4, but we don't have the magnitude, we don't have the 5. We have the 2 here, which is the Y component, the 2, which is the Z component, and the 1, which is the Y component, but we almost don't have kind of the 5, the magnitude, right? I've recreated this here. I want you to ask yourself, if we have a vector that looks like this in 3D space, how do you determine its magnitude? Well, if you weren't already, Pythagoras' theorem works just the same way as you maybe expect it to work in 2D space. So in this case, if we wanted to work out the magnitude of this vector, we would do, we would do the square root of, in this case, 1 squared plus 2 squared plus 2 squared again. So that's going to be the square root of 9, which we know is going to be 3. Okay, so we can almost add kind of like a 3-meter idea to our AD vector here. And this is going to make this force much easier to work with in this problem. Okay. So let's get started with this problem. As is always the case, if I'm to sum the forces in the X or the Y or the Z, we would expect them to sum to 0 since the system is in equilibrium. I'm drawn to resolve in the Z first. The reason I'm drawn to resolving in the Z is because we have one force acting down, which we know, and we have one force acting up, which we don't know. We're going to be left with one unknown there, which we can just solve for. Okay. So the sum of the forces in the Z are equal to 0. Things acting down are equal to things acting up. What's acting down? Well, we've got that 600 Newton force there. And what have we got acting up? Well, we've got the Z component of AD here, right? Which we could describe using our kind of geometry that we've determined here to be 2/3 of AD. So that's the Z component of AD there, okay? Evidently, AD is solvable here. We can divide by 2/3 or multiply by 3/2, same thing. So we can say, therefore, AD is equal to 3/2 of 600. Okay, and by inspection, that is 900 newtons. Okay, let's go ahead and resolve in the X then. So we can say the sum of the forces in the X is equal to 0. Therefore, things acting towards us in the X is equal to things acting against us in the X, right? What have we got acting towards us? Well, we've got the X component of AD, which we could describe as 1/3 of AD. What else? We've got the X component of AB here, which we could describe as sine 30, AB sine 30. I'm just reusing this idea that I've put in the top right corner here. And what have we got acting against us in the X? Well, we've got that AC there. Okay. Now, we know AD, it's 900, but we don't know AB, we don't know AC. We've got two unknowns here. Let's move on. Let's resolve in the y then, so we can say the sum of the forces in the y are equal to 0. Things acting to the right are equal, the forces acting to the right are equal to the forces acting to the left, right? So we have the y, things acting to the right, we have the y component of AB here, which we could describe as AB cos 30. Things acting to the left, well, we've got the y component of AD here, which we can describe as 2/3 of AD. And we know AD, it's 900. So I'm just going to say is equal to 2/3 of 900, which by inspection is equal to 600, right? So we can say, therefore, AB is equal to 600 divided by cos 30, which, when we bung in our calculator, is equal to 692.8 newtons. Okay, so we have AD, we have AB, we just need AC here, and conveniently we have a nice equation where we could just substitute those values in for AB and AD. When we substitute 900 in for AD, 1/3 of that is going to be 300. So I'm just going to write 300. We could say 300 plus 692.8 sine 30 is equal to AC. Therefore, AC is equal to, and when we bung that in our calculator, we get a value of 646.4 newtons. And those are our solutions there. So if you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.